It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our last episode, we explored the stunning power of diffusion models, watching as AI learned to generate photorealistic images and art from simple text prompts. We've journeyed through the entire technical stack, from classical search to the transformer architectures that power the large language models and generative AI that are reshaping our world. We have, in effect, learned how to build incredibly powerful, incredibly intelligent systems. But this power brings with it a new, urgent set of questions. What happens when these systems are wrong? Not just wrong in a way that produces a six-fingered hand in an image, but wrong in a way that costs someone a job, or denies them a loan, or influences a judge's decision about parole. What happens when the AI we build, an AI trained on the vast, messy, and often unjust data of human history, learns not just our knowledge, but our prejudices? This is where our curriculum must pivot. For the next 2 episodes, we are moving from the how of engineering to the why and should of ethics and alignment. This is not an optional add-on. It is arguably the most important part of your AI literacy. Because an AI system that is 99% accurate, but 1% catastrophically biased, is a broken system. Today, we are tackling the field of AI ethics. We will define what it means for an algorithm to be biased. We will explore the precise mechanisms by which bias inserts itself into our models. And we will lay out the principles of fairness, transparency, and accountability that engineers and policymakers are using to try and fix it. So what is AI ethics? At its core, it is a practical field. It's not just a philosophy class. It is a comprehensive set of values, principles, and techniques that apply widely accepted standards of right and wrong to the entire life cycle of AI technologies. This domain extends far beyond just simple regulatory compliance or technical debugging. It is fundamentally about ensuring that AI systems are developed and used in ways that are beneficial to society, upholding core human values like dignity, fairness, transparency, and privacy. Leading institutions and technology firms are building their ethical frameworks around this. They stress that AI systems must always prioritize and ensure human well-being and dignity, aiming to augment human intelligence, not just replace it. This commitment includes principles of proportionality, making sure the potential benefits of an AI justify any inherent risks. Crucially, these ethical governance models mandate human oversight, sometimes called human-in-the-loop. This is the principle that ultimate ethical responsibility for an AI system's actions must always rest with a human being. To make this real, organizations are forming specialized structures, like AI ethics steering committees, to integrate these principles of fairness and accountability directly into their products. The central problem, and the reason this field is so difficult, is that an AI system is optimized for a mathematical objective, not a human one. When we trained our models in previous episodes, we used a loss function. We were trying to minimize error or maximize accuracy, but we never added a term to that equation for fairness. We never tried to minimize injustice, and as it turns out, maximizing accuracy and maximizing fairness are not always the same thing. Sometimes they are in direct conflict. This brings us to the most common and most dangerous misconception about AI. This is a critical challenge in AI ethics. It's the belief that because AI is built on mathematics, it must be objective. People say, the algorithm is just code. It can't be racist or sexist. It's neutral. This perspective is fundamentally wrong, and it misunderstands how these models function. An AI model is a mathematical framework, yes, but it is created by people and, most importantly, trained on massive datasets. When that algorithm is deployed, it identifies patterns and correlations within this training data to make decisions. The profound difficulty arises because our historical data, especially in sensitive areas like employment, law enforcement, and finance, inevitably contains embedded systemic inequities and historical biases. The model is optimized to find efficiency and repeatable patterns. It will not minimize these historical biases. On the contrary, it will identify, codify, and operationalize them as efficient patterns for making decisions. This means AI systems function not as neutral observers, but as sophisticated amplifiers of existing social inequalities, all while hiding under the guise of scientific or mathematical objectivity. Even tiny biases in the original data can lead to widespread and discriminatory outcomes when processed at scale. The ethical imperative, then, is not just to prevent new bias, but to prevent the scaling and legitimization of entrenched old biases. So, let's define this more formally. What is algorithmic bias? It's the circumstance where an algorithmic decision creates unfair outcomes that unjustifiably and arbitrarily privilege certain groups over others. This is so consequential because algorithms are increasingly acting as critical gatekeepers, deciding who gets access to fundamental economic opportunities, affordable credit, jobs, education, and healthcare. Bias isn't a single error. It's a spectrum of problems that can be introduced, reinforced, or amplified across the entire development lifecycle of an AI system. We can break this down into 4 key stages. First, bias can enter during data collection. This is where it most often originates. If the data used to train the algorithm isn't diverse or representative of the real-world population, the outputs will be skewed. This includes selection bias, where the data is chosen in a non-reflective way, or coverage bias, where certain groups are underrepresented. Second, bias enters during data labeling. Remember, for supervised learning, we need humans to label our data. This process can introduce human decision bias, or implicit bias, based on the annotator's own prejudices. If a team of annotators is hired to label images as professional or unprofessional, their own cultural biases about hairstyles, tattoos, or clothing will be encoded directly into the ground truth labels that the AI learns from. Third, bias is reinforced during model training. This is where historical bias comes in. If the model is trained on data that is severely imbalanced, or if it's designed to prioritize existing trends, it will perpetuate the systemic inequities that are embedded in that data. The model simply learns the past as a rule for the future. And fourth, bias can emerge during deployment. Even if a model seems fair in training, it can become biased when it's deployed in the real world and interacts with a complex, dynamic environment, leading to feedback loops. One of the most insidious ways this bias manifests is through the use of proxy variables. This is a concept you must understand. Recognizing the ethical and legal problems with using protected attributes, like race, gender, or religion, many developers try to achieve fairness through unawareness. The idea is that if you just remove the race column or the gender column from your dataset, the AI can't be racist or sexist. This approach is widely considered naive and completely ineffective in the machine learning community. Why? Because AI models are extremely good at identifying other, seemingly neutral inputs, the proxy variables, that are highly correlated with the protected attribute you removed. For example, in many American cities, Zip codes are a very effective proxy for race and socioeconomic status. A person's name, or their specific consumer behaviors, can also serve as powerful proxies. The algorithm, in its quest to find the strongest patterns, will find these correlations and use them. The causal chain is this: historical inequality leads to skewed data. The AI model, even when blind to the protected attribute, finds and optimizes for the proxies that replicate that skew. This creates a significant tension. Legal precedents often favor decision-making that is blind to protected attributes. But as we'll see, effective technical bias mitigation, the act of fixing the bias, often requires the developers to know and use these sensitive attributes to measure and correct the disparities. If this correction step is prohibited, an algorithm might be considered legally permissible, even while being technically and morally biased. This isn't theoretical. Let's move from the how to the what. What are the real-world consequences? I want to detail 2 landmark case studies that show just how high the stakes are. First, let's look at hiring. In 2018, it was widely reported that Amazon had to scrap an AI recruiting tool it had been building. The goal was simple. You feed the AI 100 resumes, and it spits out the top 5 candidates. To train it, they fed it the company's own hiring data from the previous 10 years. But as we just discussed, that data was historically biased. The tech industry, especially in that period, was predominantly male. The algorithm interpreted this male dominance as a pattern indicative of success. Consequently, the automated system learned to penalize applicants whose resumes included female-specific terminology. It penalized resumes that contained the word women's, as in captain of the women's chess club. It even reportedly downgraded graduates from 2 all-women's colleges. The engineers at Amazon tried to go back and teach the AI not to be biased against these terms. But they couldn't be sure they had found all the ways the AI had learned to infer gender. The model was learning subtle cues in language and phrasing that correlated with gender. Amazon ultimately disbanded the team, deciding the system was not fixable. This case demonstrates how a model, tasked with optimizing for past patterns of success, can inherit undesirable human traits and perpetuate gender discrimination. Our second case study is in healthcare. This demonstrates the danger of proxy variables in a high-stakes decision. In 2019, a major study in the journal Science uncovered widespread racial bias in a healthcare algorithm used by hospitals across the United States. This algorithm was used to identify high-need patients who would benefit from high-risk care management programs that provide extra resources and attention. The algorithm's goal was to predict which patients would have the highest health needs in the future. But health needs is a fuzzy concept, so the designers used a proxy. What proxy would you use? They used prior healthcare expenditure. It seemed logical. People who are sicker cost the health system more money. But this proxy is deeply biased. Because of systemic inequities and historical barriers, less money is spent, on average, on black patients than on white patients, even for the same level of sickness. This can be due to a lack of access, or doctors taking their pain less seriously, or any number of other factors. The result: a black patient and a white patient with the exact same chronic illnesses would have different predicted costs. The algorithm would see the lower cost for the black patient and incorrectly conclude that they were healthier and in less need of help. The study found that this bias was massive. It reduced the number of black patients admitted to these critical care programs by more than half. The researchers found that if this bias were corrected, the percentage of black patients receiving this extra help would jump from 17% to 46%. This is a perfect example of a seemingly neutral economic choice using cost as a proxy for need, having deeply discriminatory and harmful consequences. So, these examples are sobering. They show that bias isn't a small glitch. It's a fundamental failure mode of AI systems trained on human data. The obvious next question is, what do we do about it? This brings us to the core principles of ethical AI, and our first one: fairness and non-discrimination. This sounds simple, but it is technically and philosophically one of the hardest problems in all of computer science. Why? Because what does fairness actually mean? This is the challenge of operationalizing fairness. We have to move from a qualitative ethical goal to a quantitative, measurable metric. This is hard because fairness is not a singular, neutral ideal. It is a socio-technical construct, which means we have to make explicit choices among competing mathematical definitions. These definitions are generally formulated using the basic concepts from classification. True positives, which is a correct yes prediction; true negatives, a correct no; false positives, a wrong yes; and false negatives, a wrong no. The choice of metric is paramount because it determines which specific errors the system prioritizes minimizing, and consequently, which group bears the greater burden of the algorithm's inevitable mistakes. You might be surprised to learn that there are over 20 different mathematical definitions of fairness that researchers use, and, critically, many of them are mutually exclusive. You cannot satisfy all of them at the same time. Let's use our loan application example to understand three of the most common ones. An AI is built to approve or deny loans. Let's imagine two groups of people, Group A and Group B, are applying. One definition of fairness is demographic parity. This is also known as statistical parity. It requires that the probability of receiving a positive outcome, in this case getting the loan, must be equal across all groups. Mathematically, this means the probability of the AI saying yes, given that you are in Group A, must equal the probability of it saying yes, given that you are in Group B. If 50% of Group A is approved, then 50% of Group B must also be approved. This metric is designed to address allocation harms, the unequal distribution of resources. But its simplicity is its weakness. What if, due to historical economic factors, the applicants in Group A have, on average, much higher credit scores? To meet its 50% quota for Group B, the AI might have to approve people with very low credit scores, while denying people from Group A who had better scores. This is fair to the group, but deeply unfair to the individual. A second, more subtle definition is equal opportunity. This metric focuses only on ensuring that qualified individuals have an equal chance of receiving a positive outcome. It says that among all the people who would successfully pay back the loan, the qualified people, the AI should approve an equal percentage from both groups. In other words, the true positive rate must be equal. The probability that the AI says yes, given that you are actually qualified, must be the same for Group A and Group B. This sounds much better, right? We're ensuring fairness among the qualified. But it doesn't address any disparities in false positive rates. That is, it doesn't care if it wrongly gives loans to unqualified people at different rates across groups. This brings us to a third, stricter definition: equalized odds. This is considered one of the most stringent criteria. It requires that the model performs equally well for different groups, conditional on the actual outcome. To satisfy equalized odds, the model must achieve both an equal true positive rate and an equal false positive rate across all groups. This addresses both allocation harms and quality of service harms, where a system might work reliably for one group but fail frequently for another. So which of these is fair? Demographic parity, equal opportunity, equalized odds? There is no single correct answer. This is the critical takeaway. Deciding which definition of fairness to use is not a technical problem. It is a societal and policy problem. Engineers can't decide this. We, as a society, have to define what we mean by fairness in a given context, and then the engineers can code that specific definition into the system. Now, let's look at the preeminent example of the incompatibility of these fairness metrics. This is the debate surrounding the proprietary compass algorithm, which, as we mentioned, is used in U.S. criminal justice systems to predict a defendant's risk of reoffending. In 2016, the investigative journalism group, ProPublica, conducted a detailed analysis of the compass scores. What they found was that while the algorithm's overall predictive accuracy was statistically moderate, the distribution of its errors was severely racially biased. Here are the critical findings. The algorithm disproportionately committed two different types of errors against two different groups. First, it had a much higher false positive rate against black defendants. Black defendants were falsely flagged as future criminals. That is, they were assessed as high risk, but did not go on to reoffend, at nearly double the rate of white defendants. The study found the false positive rate was 44.9% for black defendants versus 23.5% for white defendants. In this context, a false positive can lead to higher bail or a more punitive sentence for someone who was not a high risk. Second, it had a higher false negative rate against white defendants. White defendants were mislabeled as low risk. That is, the algorithm said they were safe, but they did go on to reoffend more often than black defendants. The study's numbers were 47.7% for white defendants versus 28.0% for black defendants. A false negative means a person who may be a danger is wrongly assessed as low risk. The algorithm's creator, Northpoint, defended its system by pointing out that it satisfied a different fairness metric, called predictive parity, which means that for any given risk score, the percentage of people who reoffend is roughly the same, regardless of race. Here is the mathematical reality. In scenarios where the underlying base rates, the actual rates of reoffending, are unequal across groups in the data, an algorithm cannot simultaneously satisfy all definitions of fairness. It is mathematically impossible. This forces an explicit ethical choice. Do you want to equalize the false positive rate, which would reduce the number of black defendants who are wrongfully accused, or do you want to equalize the false negative rate, or do you want to maximize overall accuracy? The compass case showed that, despite similar overall accuracy, the system failed on the grounds of error equity, distributing the burden of its mistakes unfairly. So, how do we technically fix this? If we identify bias, what can we do? The mitigation strategies are typically categorized by when in the AI lifecycle the intervention occurs. First, there are pre-processing algorithms. These methods focus on modifying or adjusting the dataset before it is used to train the model. Techniques include augmenting the training data, resampling it to address missing or skewed representation, or otherwise ensuring the input data is fairer, which in turn helps yield a fairer model. Second, there are in-processing algorithms. These methods act during the model training phase by modifying the algorithms themselves. This often involves adjusting the model's optimization function, that loss function we keep talking about. We can add regularization terms or constraints to the loss function that explicitly penalize the model for discrimination based on protected attributes. Third, there are post-processing algorithms. These methods calibrate or adjust the final results after the model has already made its decision. A common technique involves setting different prediction thresholds for different groups to achieve a specific fairness metric, like equalizing the true positive rates. For generative AI, this can involve implementing screeners to detect and filter biased or inappropriate content, like hate speech, from the output. This leads us to the second core principle for ethical AI: transparency and explainability. This is the antidote to the black box problem. Remember when we discussed deep neural networks, back in part 4 of our curriculum? We talked about how they are incredibly powerful but also very complex. A black box model is a predictive system that is either too complicated for any human to fully comprehend, like a deep neural network, or it's proprietary, where the specific logic is intentionally undisclosed. When these black box models are deployed in high-stakes areas, justice, finance, healthcare, the ethical danger is severe. If the algorithmic rationale is hidden, it becomes impossible for affected individuals to trust the predictions, appeal incorrect decisions, or even determine what factors the model considered. "The computer said so" is not an acceptable answer. We need to be able to ask the AI to show its work. This is the field of explainable AI, or XAI. It's a set of techniques designed to make AI models interpretable, to improve trust, and to enable debugging. But within XAI, there is a significant chasm between two different approaches. On one side, you have post hoc explanations. This involves creating a secondary model, using techniques like LIME or SHAP to explain the predictions of the complex, opaque black box model. The ethical critique here is profound. Since the explanation is derived from a different model, it may not be entirely faithful to the original black box's true computation. These explanations can omit crucial details or generate summaries that are misleading, especially if the black box is relying on spurious, nonsensical correlations. On the other side, and this is what the ethical imperative favors, you have inherently interpretable models. This is about designing models that are interpretable from the outset. These are generally simpler, constrained models, like simplified regression models or decision lists, where their computation is directly understandable to humans, making their explanations automatically faithful. And here is the critical insight. For many high-stakes domains, especially those with structured data, the perceived trade-off between model accuracy and interpretability is often a myth. Simpler, interpretable classifiers often show no significant difference in performance compared to complex black boxes. For any high-stakes application, the marginal gain in accuracy from an opaque model is ethically and legally outweighed by the necessity of an interpretable, verifiable rationale. The third and final principle is accountability and human oversight. This is the ultimate backstop. It's the principle that no matter how smart an AI gets, humans must remain responsible for its outcomes. This is often implemented as human in the loop. For the most critical decisions, a medical diagnosis, a parole decision, firing a weapon, the AI should never have the final say. It can be a powerful assistant. It can analyze the data, highlight risks, and present a recommendation. But a qualified human being must make the final judgment. This isn't just a concept, it's being codified into governance and accountability frameworks. This requires robust organizational processes. It means mandatory documentation and continuous risk assessments. developers are now being required to document and share information about their system's limitations, its intended uses, and the risks they've evaluated. Frameworks like the NIST AI Risk Management Framework or the ITI AI Accountability Framework provide a structured approach for organizations to incorporate trustworthiness and manage risks related to bias and fairness directly into the design, development, and use of their AI products. So, as we bring this all together, we can see a symbiotic ethical toolkit emerging. A trustworthy AI system requires three simultaneous actions. First, we must identify bias through continuous auditing of our data and our model outputs, searching for inequities and proxy discrimination. Second, we must quantify fairness, making explicit ethical choices about which mathematical fairness metric, like equalized odds, is most appropriate for a specific context. And third, we must ensure accountability through mandatory transparency by prioritizing inherently interpretable models for high-stakes decisions and by implementing formalized governance and human oversight. The analysis strongly recommends continuous human oversight at every stage. It requires embedding ethics experts into the design process from day one, and it demands that we subject our models to continuous auditing and evaluation based on their real-world performance. This entire episode has been about the ethics of AI, which is really about the present. It's about the harms we can see today in systems that are already deployed. And this connects directly to the powerful models we just finished studying. When we talked about large language models, we discussed how they are trained on a massive snapshot of the internet. Think of the bias in that data. These models learn to associate doctor with he and nurse with she. They learn to associate certain races with crime and certain religions with terrorism. This isn't malice, it's associational bias learned from petabytes of biased human text. When we talked about generative image models, we saw their power. But what happens when you type a CEO and it only generates images of white men? Or a nurse and it only generates women? This is a direct reflection of the data bias in the training set. Companies building these models are now spending enormous effort on post-training to try and steer these models toward more equitable and representative outputs. These issues, fairness, bias, and justice, are about the harms we can see today. But there is another, larger conversation that looms over all of this. It's not just about making our AI fair, it's about making our AI safe. As these systems move from being powerful tools to being potentially autonomous agents, as they become smarter and more capable, we face a new, more existential question. How do we ensure that an AI's goals are truly aligned with human values and with human survival? This isn't about bias in a dataset. This is about the fundamental objectives we give to a system that could one day be smarter than we are. This is the alignment problem. And that is where we are heading. We've built the technical foundation. We have now established the ethical framework for the present. In our final episode, we will look to the future and tackle the single biggest, most important, and most difficult question in all of artificial intelligence.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.